Today we're talking about types of reactions. So there's a synthesis reaction. So in a synthesis reaction, we have two or more things combined to form one larger thing. Okay? Like baking a cake, where you take all the ingredients and then you get a cake at the end. Synthesis means build. So synthesize, build, synthesis, build, make a bigger thing. Okay, so here you can see synthesis happening. So we take two reactants, one product. Two reactants, one product. Synthesis. Two reactants, one product. Synthesis. Here are some other examples of synthesis reactions. Now, a decomposition reaction is the opposite of synthesis. So we take one reactant and break it apart into two or more products. One reactant broken apart. Decomposition or decompose is to break apart. So here we can see a decomposition reaction in progress. One reactant broken apart into more than one product. One reactant, more than one product. Decomposition. Decompose. Break apart. Decomposition. Here are some additional examples of decomposition reactions. Now, a single replacement reaction is where we have a single element and a compound, and on the other side we also have a single element and a compound, but they've switched places. So if you were partnered with Caroline and Antonio was working alone, and now you are partnered with Antonio and Caroline is working alone. So single replacement, why? Solo, single. We have a single element on this side and a single element on this side, but they're different because they've swapped places in the compounds. So we start with element and compound and we end with element and compound. There's just been a switcheroo. So here you can see single replacement in action. In this type of reaction, we have single elements on both sides, but different, and compounds on both sides, but different. What happens is the elements switch places. So in one, iron is alone. On the other side, iron's in the compound. In one, copper's in the compound, and on the other side, it's alone. We have a switch. So we always have a single element and then a compound on both sides, but you can see they've swapped places. Okay, so here you can see that chlorine and iodine have swapped places. Here you can see that potassium and hydrogen have swapped places. And here you can see that zinc and hydrogen have swapped places. Now, double displacement reaction is the most complicated looking one. It's where there's all compounds, and all that happens is elements switch again, but it's two compounds on one side and two compounds on the other side, and the elements switch places again. So it's just like swapping partners. So you were partnered with Caroline and Antonio was partnered with DeMarcus, and now we've swapped partners. So double replacement, two compounds, double on both sides. So two compounds on one side, two compounds on the other side. There's just been a switch. So let's see what it looks like. Here we can see one in action. Again, two compounds on the reactant side, two compounds on the product side, but we have elements swapping places, so the compounds end up different on both sides. Here we can see some examples. You can see that potassium and silver have swapped places. Sodium and strontium have swapped places. And hydrogen and sodium have swapped places. So looking at this reaction, which kind of reaction do you think this is? Well, let's look at it. Well, we have two things on this side and one on this side. Yes, it tells us energy is here, but that's not a chemical formula. So this is, yeah, synthesis. Follow-up question, I circled where energy is. Is it exothermic or endothermic? Yeah, it's exothermic because energy is on the product side. It's being released. Let's look at this equation. What kind of chemical reaction do we have here? Well, let's look. We have two things on this side and two things on this side. So I know it's not synthesis and I know it's not decomposition, right? So what do I have? Oh, look, single element, single element. Yes, there's a subscript, but that doesn't change that. It's still one element. Single replacement. All right, what do we have here? Well, I've got two things on this side and two things on this side, so it's not decomposition and it's not synthesis. So everything's a compound, double replacement. All right, what about this one? Well, I have one thing on this side and two on this side. Oh, that's breaking apart. That's decomposition. Now, there are also organic reactions, okay? So I like to use the phrase PS faces as an acronym to remember the first letter of each of the organic reactions. So I have P, polymerization, S, saponification, F, fermentation, A, addition, C, combustion, E, esterification, and S, substitution. Yes, there's two S's, so it doesn't matter where I put them, but in my head, I always think saponification first. First up, we have polymerization. That's the P. So a polymer is a big molecule that's made from a chain of monomers, and the monomer is the little molecule. The process is called polymerization, where we join a bunch of monomers to produce a polymer. Here's an example of what it might look like. So monomer, 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 this is a representation of the polymer. Monomer with an N, like a big number, then you can see here these open bonds at the end indicate they're connected, and that big number is going to be over here. So we make a huge chain. Saponification is making soap. And if you just look at the letters in soap and look at the beginning of saponification, it's soap, but just a little switched. Okay, what you need is a fat and a strong base in order to make soap. So the base is the key thing. So table L lists common bases, and what you notice is that they all end in OH. Now this base is listed here, but it's a weak base. It's the only weak base in this table. So that basically means I'm looking for something with an OH, or like that. See that? Base, soap. So it's not going to have these words that tell you soap. So what process makes soap? Saponification. How can you tell it's saponification? Look for a base as a reactant. Fermentation. So this is the process where alcohol is made. So we take sugar plus yeast, so we need a catalyst, and we get alcohol and carbon dioxide bubbles. Okay. Now, alcohol, how do we know it's an alcohol? Well, this is from table R in the reference table, and it has this for alcohol as its functional group. That means an alcohol has an OH, but it's not going to be listed with the bases, okay? So it's going to have like carbons and hydrogens and then an OH. So it's organic with an OH. That's an alcohol. Organic with an OH is an alcohol. But the other clue is we get bloop, 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 carbon dioxide bubbles. All right, addition. Well, when you add, right? So in this case, we have to break a double bond of something that's unsaturated. Typically, it's a double bond, but it could technically be a triple bond. But let's just talk about a double bond. So we break a double bond, and we add two atoms to replace where that double bond was. Usually, we add hydrogen or a halogen, so something in group 17. So let's look at an example. So here what we do is we break this bond, and now there's two open spaces, and we put those two things in the open spaces. Break this bond. Now there's two open spaces for bonds, and we put the bromines there. Combustion. We learned this already. It's where an organic compound burns in the presence of oxygen and produces carbon dioxide and water. Combustion is burning. Now here you can see a combustion reaction happening. We burned some things in class and saw the process happening. we have something with carbon and hydrogen combined with oxygen, and it produces carbon dioxide and water. Here are some additional examples of combustion reactions. Getting near the end, it's the E, it's esterification. So here we make an ester. It's not shocking, look at the name. Esterification makes an ester. What is it? Well, esters are things that like make sense. So like banana flavored candy and strawberry flavor and vanilla scented. Okay, so they're smells. Those are esters. Okay, and we make it from an acid and an alcohol, and we make an ester, and we also get water out in the process. So if I look here again, table R also lists esters. So for esters, I'm looking for this. So right here, see this? Bloop, 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 that's an ester. Okay, this OH looks like it's supposed to be an alcohol, but this actually COOH together, that makes an organic acid. This OH is the alcohol. But ester, that's what you should be really looking for. Ester, right? And water, okay? And finally, the last S, substitution. So in substitution, just like in a game, one comes out and another one goes in its place. So that's what happens. So here, in this reaction up here, all hydrogens attach to the carbon, and then what happens is one of the chlorine comes and takes the place. All hydrogens, a bromine comes and takes its place. All hydrogens, a fluorine comes and takes its place. So one swap-a-roo, substitution. And now balancing equations. So let's review a little bit about equations and what you should know about balancing. So first, you should know the difference between elements and compounds. You should know that elements cannot be broken down by chemical means, but compounds can because they have chemical bonds. You should know that elements are one kind of an atom. It can have a subscript, but all of the kinds have to be the same. So it could be O2 or O3, that's still an element. A compound has two different elements combined, so like NaCl, okay? And sometimes they have subscripts and sometimes they don't, okay? States of matter, you should know S, solid, L, liquid, G, gas. When you see AQ, that means dissolved in water. So it is a mixture. So it's not a pure substance, it's a mixture. In fact, everything is either a pure substance or a mixture. Pure substance meaning element or compound, and mixture meaning heterogeneous or homogeneous. All right, now we can have both subscripts and coefficients. Subscripts tell you how many atoms of an element are in a chemical formula. Coefficients tell you how many of that molecule you have. So in this case, this 2 in front here says I have 2 of these. So in fact, I have 4 total H's because 2 times 2, okay? So again, when we count atoms, the subscripts matter and the coefficients matter. The coefficients have to get distributed to everything by multiplication, and the subscripts outside of parentheses have to get distributed to everything inside the parentheses. We say arrows as the word yields. We don't say points to or arrow or something like that. We say yields. You could also say produces, most commonly yields. The difference between reactants and products, reactants on the left side, products on the right side. The difference between exothermic and endothermic, which you know table I tells you at the bottom a minus sign indicates exothermic. But when we see energy or heat or calories or joules on the reactant side, energy is coming in, endothermic. When we see heat or energy or joules or calories on the product side, energy is leaving, it is exothermic. Here's a lot of it put together. Reactants on the left side, products on the right, yield is the arrow. We have coefficients, which tell us the number of molecules. We have subscripts that tell us the number of atoms. And we have states of matter indicating the state, or phase. Remember, state of matter, phase of matter. All right, now let's balance. So the first rule of balancing is that you only change coefficients. You can't change subscripts. If you did, you could turn water into hydrogen peroxide. That's a big no-no. So we can only change coefficients. We can only add coefficients in front. We can't change chemical formulas. So some things to remember. Coefficients have to be in the smallest whole number ratio possible. So here's an example. In this equation, if it were balanced like this, okay, let's look at the ratio of the coefficients. 16 to 3 to 8. Well, I can't divide all those numbers by anything except for 1, right, to get a whole number. So it is the simplest ratio. It can't be reduced. I'm done. Let's look at another example. So say here is the chemical formulas, the equation, and say I balance it like this. Let's look at the ratio. It's 6 to 2 to 2. Well, this is not the simplest ratio. I can in fact divide all of those numbers by 2. So when I do that, I get a reduced ratio of 3 to 1 to 1. And so it would look like this. Remember that I can write a 1 here, but that if there is nothing in the blank, it's a 1. So you can write the 1 or leave it blank. Never, ever, ever write a 0. You just erased it. There has to be conservation of mass or matter when we balance. So that means the total number of elements on both sides has to be the same. We have 4 ions on this side and 4 on this side. 6 oxygen, 6 oxygen, 3 carbon, 3 carbon. That's when it's balanced, when we have the same number on both sides. Now you have to be careful when an element is in more than one formula on the same side. So here you can see that oxygen is in 2 different formulas, right? So if I put a coefficient here as an example, say I put a 2 here, it would not change all of the oxygen. It would only change this oxygen that's here, okay? So we have to kind of separate them when we are balancing so that we don't mix them up. And you can see that represented here by the 10 plus 1. So if I put a coefficient in front of the P4O10, I would be multiplying this one. But when that 6 goes in front of that one, I multiply that one by 6, okay? And once I put that 6 here, that 6 has to be multiplied by this hydrogen and this oxygen. If you're ever stuck, a good suggestion is this. When you have an element that's in an even odd pair, do you see that 2 hydrogen on this side and 3 on this side? Start by making the odd one even by multiplying it by 2 and then try and finish the balancing. All right, and the next thing I would say, if you're struggling, try putting a 2 as the coefficient in front of the most complicated formula or the one that has the most elements in it. And in this case, it would be this one, put a 2 here, and then amazingly, when you work through everything, you can get it to balance that way. So that's a good place to start. If 2 in front of the most complicated formula doesn't work, you can always try 3 or 4, or try a 2 in front of a different formula to start. But sometimes when you're stuck, it helps you get started. Now, a big part of balancing is practice, practice, practice. So let's look at some examples. All right, so here we have potassium, oxygen, and hydrogen, and bromine on both sides, right? Now let's count how many we have. So we have 1 potassium, 1 oxygen. I have 1 plus 1 for hydrogen, right? So that's 2. I have 1 bromine. Here I have on this side, so I'm looking over here, 1 potassium, 1 bromine, 2 hydrogen, 1 oxygen. What do you notice? Yeah, it's already balanced. Sometimes it is. So I could leave all of those lines blank or put a 1, a 1, a 1, a 1. All right, now let's do the next one. So we have sodium and oxygen on both sides. Let's count. Here's my divider, right where the arrow is. So 1 sodium, 2 oxygen. On this side, I have 2 sodium, 1 oxygen. Okay, so it's not balanced, right? Now, I'm going to try and balance first the one that has more than one element in it, so here. I have one oxygen over here and two over here, so let's fix that. So that means I have two oxygens now, right? But I also have to multiply the sodium times 2. So oxygen is fixed, but sodium is not. So, but if I put a 4 here, I would multiply the sodium by 4, and I'm balanced. I could put a 1 here, right? Or leave it blank. This kind of reaction is what? This is synthesis, right? Why? Because I start with 2 things, and I end up with 1. I built something, okay? All right, so here's the hardest example that we're going to do right here, okay? Notice I kept CO3 as a group. Why? Because it's in parentheses here and then also over here. Now, it's not in parentheses because there's just one of them. So technically, if you wanted to, you could do this and put a 1, okay? So I'm going to make my list. Now I'm going to count. 1 aluminum, oxygen is 3, hydrogen is 3 there, plus 2, so that's 5. 1 of those, 2 of those, 1, 2, and 3. Whew, this is like a hot mess here. And I'm just going to pick something to start with. I'm going to do CO3 because that looks complicated. So I'm going to multiply it times 3. That's 3, right? So when I do that, I also multiply this hydrogen times 3, which gives me 6, which now gives me 9. Well, I'll only fix that. Great. All right, let's try aluminum next. All right, so I multiply it times 2, right? Put the 2 here. What does that change? Also the oxygen times 2. Also this hydrogen times 2, so that's 6 and 6, which is 12. Okay, so we have aluminum balanced and CO3 balanced. That's something. How would we balance the oxygen? Put a 6 in front, right? So times 6 equals 6, which also multiplied the hydrogen times 6, which is, oh, 12. Look at that. So it's balanced. This, I could put a 1 or leave it blank. So now there's more practice for you to do, but those are some examples.